Hey guys, today I'm going to teach you all about percent error. By the end of this lesson, you will be able to calculate percent error. Go ahead and get out your notes and be ready to learn. Let's get started with some vocabulary. Absolute error measures the difference between the approximate or accepted value and the exact or measured value. Absolute error can be solved by finding the absolute value of the difference between the approximate value A and the exact value V. We will use this in the next couple of questions to find the absolute value. Number 1 says a science experiment calls for 150 milliliters of water, but Simon measures out 147 milliliters. What is the absolute error? To find the absolute error, I'm going to take the approximate value, which is 150. That's what the experiment called for. And I'm going to find the difference or subtract what Simon actually measured, which is 147 milliliters. When I get the difference, I get that it is the absolute value of 3, and the absolute value of 3 is 3. So for this, the absolute error is 3 milliliters. In question 2, a student measured the mass of an object to be 56 grams, but the actual mass was 53 grams. What is the absolute error? In this problem, the actual value was 53 and the measured mass was 56. The difference of 53 minus 56 is negative 3. We know that the absolute value is distance from 0, making it always positive, so in this case the absolute error is 3 grams. Next we will look at percent error. Percent error compares the absolute value to the exact value. For example, when calculating the mass of an object in science, measuring the distance an object has traveled, etc. Percent error can be solved using a percent error equation in which the values are plugged into the formula below. Let's look at question 3. Question 3 says, during a school assembly, Mrs. Quinn takes attendance and counts 356 students. In actuality, there are 376 students. What is the percent error? I will use the formula that we were given at the top to set up a percent proportion to solve for the percent error. To set up this proportion, I'm solving for the percent, so that is my unknown, that's where I have a variable, and percents are always out of 100. In the other half of my proportion, I know in the numerator I need to find the absolute value of the difference between the approximate and the exact amount. I know that the approximate amount is how many students were counted, which was 356. And the actual or exact amount is the 376 students that there are. Then we divide that by the exact amount, which is also 376. When I take the difference, I get negative 20, but we're looking for the absolute value, which is positive 20. And now we have a percent proportion that we can solve. After cross multiplying, I find out that my percent error is 5.3%. The next question says, in a crowded sports arena, 250 seats are counted. If there is a 20% error on the count, what is the range of acceptable number of seats? In this problem, we can use the same percent proportion. We just have a different piece of the information that we are solving for. I set up my proportion with my 20% error over 100 set up equal to my unknown, which is the range of acceptable number of seats, over the amount of seats that there actually are, which is 250. After solving, I get that x equals 50, but I actually need to use this to figure out what that means for my percent error. This means that the difference between the approximate and exact number of seats is 50. This means that our seats can range from 200 to 250 or 250 to 300. So in total, our seats can range from 200 to 300 seats. We'll look at the next set of questions to find the absolute and the percent error in this situation. The next question says, several students are competing in a science club competition to build a car that will travel exactly 10 meters. The distance each student's car traveled is shown in the table below. We're going to use this information, first of all, to find absolute error for each person's race car, and we'll start with Emily. For each person's race car, the exact value is going to stay the same at being 10 meters, as stated in the problem, that's what the car should go. Next, we need the approximate value, that comes from what actually happened in the experiment. Sometimes it's called the experimental or the measured value, which I think is sometimes easier to pair with what happened in the experiment. In this case, Emily's car traveled 9.2 meters. The formula for absolute error is to take the absolute value of the difference between the approximate or measured value and the exact value. In this case, that is 9.2 minus 10, which we know would give us negative 0.8, but we're looking for the absolute value, which gives us Emily's absolute error of 0.8. Next, we can look at Jerome and use the same exact process to find his absolute error. What we want to notice is that our exact value stays the same. Each time, the exact value is going to be 10 meters. That's what should have happened. In this case, we're going to take Jerome's measured distance of 10.6 and subtract the exact distance of 10 meters to get 0.6. This is Jerome's absolute error. Finally, we can find Maricella's absolute error using the same formula. In this case, her measured value is 9.8 and the exact value stays the same at 10. Once we find the difference, we get that absolute error is 0.2. For percent error, I'm going to go to a different slide just so that I have a little bit more room to work out the problem. From the beginning of our notes, we need to use our percent error formula. The percent error formula is to take our absolute error and divide that by our exact value. And then remember that to find the absolute error, which in this case is the numerator, we take the difference between the approximate value and the measured value or exact value. Now that we have our formula again, let's get started with this problem. We're looking for the percent error for Emily's race car first. For Emily's situation, we use her approximate value. That's how far her car actually traveled, which was 9.2 meters. Remember that the approximate is also the same as the experimental, or what happened in the experiment. And then the exact is what we were shooting for, or what was supposed to happen. In this case, each car was supposed to be able to travel 10 meters. So we take 9.2, subtract that exact value of 10, and then divide by the exact value of 10. We really had already found our numerator, since that is the same thing as finding the absolute error, and we know that that is 0.8 once we take the absolute value of that difference. Then we want to divide that by our exact value of 10, and we get 0.08. However, we're looking for percent error, so this time we didn't set up a percent proportion, kind of like we had in the past. We used the formula where we're just getting our percent error. So I need to actually change this decimal into a percent. When changing a decimal to a percent, we move our decimal 2 places to the right. This gives us an error of 8%. We'll do the same thing for Jerome, but I'll show you what I meant by using the percent proportion so that we don't have to change that decimal into a percent just in case we were to forget that last step. In this case, I want us to recognize that the numerator of our second fraction is going to be the absolute error that we already found. And the absolute error that we already found for Jerome was 0.6. And again, I want to recognize that that exact value is still the 10 that the car was supposed to travel. When setting up a percent proportion, I'm using the same piece from the formula that we just used, but I'm setting it equal to another fraction, the fraction that we've been using, percent out of 100. In the formula, I did change that percent to a variable since that is the piece that we're solving for. So now I had x over 100 equals 0.6 over 10, and then we just find our cross products and solve for that unknown. When I solve for that unknown, I get that our percent error is 6%. Next, I'm going to go through the entire process of finding Maricella's percent error. This time I'm going to use the percent proportion again. Remember that on the left side of the fraction on the left side, we're looking for the percent out of 100. The percent in this case is our unknown. We're looking for that percent error, so I'm using a variable there. On the right side of my proportion, I'm going to look for my absolute error. To find that, I'm going to take the absolute value of her measured or experimental value, which was 9.8, and subtract the exact value that we've had this whole time of 10 meters. That's what we wanted the car to be able to go. And then we're going to divide that by the exact value of 10. Before cross multiplying though, I want to simplify that top numerator since I can find the absolute error that we already found was 0.2. Now I can use my cross products to solve for percent error. After cross multiplying, I find that my error is 2%. Now that we have each person's percent error, we can start to answer some of these questions. The first question says, based on this information, what does a small percent error indicate? With percent error, we're seeing how close our experiment actually came to what we were trying to come to. In this case, we're seeing how close our cars actually came to the 10 meters they were supposed to go. When we're doing percent error, a smaller percent error would indicate that the car is built closer to the needed specifications and can travel very close to 10 meters. In this case, it looks like Jerome's car is the only one that can go 10 meters or further, but really, Maricella's is closest to the 10 meters at 9.8. Next, we'll look at these statements and using our percent error determine if they are true or false. The first statement says Jerome has the smallest percent error. So looking back at my part B, it looks like our percent error for Emily is 8, Jerome is 6, and Maricela is 2. So Jerome does not have the smallest percent error. Next question says Emily's race car was the most accurate. For it to be the most accurate, we would want the smallest percent error, or the closest to 0. This means Emily's race car is not the most accurate. Hers is actually the farthest from accurate with the greatest percent error. We'll look at the last one. It says Emily and Maricela had a negative percent error because their cars traveled less than the desired distance. This is also false since we found the absolute value. It's going to be positive, and in this case, we just have 8% and 2%. And we can determine what those mean by looking at how close they are to 0 for the percent error. Let's look at the last question together. It says, Mr. Brown's class was guessing the number of gumballs in the gumball machine in the cafeteria. All of the guesses were between 382 and 456. After counting, it was determined that there were actually 408 gumballs in the machine. First, we're going to look at the absolute error. Remember, absolute error is to find the absolute value of the distance between the approximate and the exact values. In this case, the approximate value is 382. That's the first guess. And the exact value is how many actual gumballs there were. In this case, there were 408 gumballs. When I find this difference and the absolute value, I get 26. Go ahead and find the absolute error for the next guess, and then press play when you're ready. The absolute error for this problem was 48. Let's look at percent error next. I'm going to set up a percent proportion for this problem just so that I don't forget to change that last decimal into a percent. In this case, I'm also going to take that percent from the top of my proportion and make it my variable because that is what we are solving for. Remember that the denominator of our second part of the proportion is going to be what the gumballs actually was, how many there actually were, which was 408. After getting my cross products and solving, I get that my percent error is going to be 6.37. There were some other numbers past the decimal on my calculator, but I didn't want to write those out because I knew that I was going to be rounding. And I'm just going to go ahead and round to the nearest tenth. So I'm going to look in my problem and see that I've got 3 and then 7, and know that that 7 is going to make it round up so that my percent error is 6.4%. Go ahead and pause the video and try this for the next number. You can check your work with mine off to the right, but I got that my percent error for the second guess was 11.8%. We can then look at our two different percent errors, and we can see that the guess of 382 was actually closer to the correct number of gumballs in the machine. That's it, guys. If you made it to the end of the video, tell us where would you like to go on vacation. Today we went over percent error, so now you should be able to use our percent error formula or set up a percent proportion to calculate percent error. You should also be able to use percent error to determine what that means in a situation. With percent error, we're looking to get closer to 0. Indicate less of a percent error. Let me know if you have any questions. Bye, guys.